SwayamPrabha. Digital India. Educated India.
Very good morning. I welcome you all to the session of thermal engineering, basic and applied, and today we shall discuss about gas turbine unit, those run using a combined cycle concept. So, in the last class we have talked about the multi-staging and we had discussed the need of multi-stage compression, and also we had seen that for the multi-stage compression intercooling is a must, and we had seen that in a multi-stage compression with intercooling we could save certain amount of work to run the compressor, and it is intuitively expected that saved work will certainly increase the cycle efficiency. So, today we shall discuss that again from the perspective of the process diagram, and if we map all those processes in a TS plane. Now, for the recapitulations what we have discussed, we have discussed that air which is drawn into the compressor, that air is compressed. Now, we need to run gas turbine units having certain pressure ratio. Higher the pressure ratio, just by looking at the mathematical expression of the cycle efficiency, we can easily understand that with increasing pressure ratio efficiency will increase, and if we need to achieve a higher pressure ratio, it is also doable by using a single stage compression. But as we have discussed that if we consider single stage compression, certainly we can build that pressure, but at the exit of the compressor temperature rise will be so high that rise in temperature which is associated with the rise in pressure will lead to the damage of several mechanical components of the compressor. Not only that, this when that gas temperature or temperature of any other working fluid increases, and if we need to go for multi-staging, of course, we need to go for intercooling, because it is easier to compress high density cool air than the hot air. So, multi-staging is essentially an important aspect of the compression process, wherein we need to compress at a high pressure, and such a pressure will lead to an increase in temperature, and that temperature may be vulnerable to several mechanical components, and we need to go for multi-staging. So, for the brief recapitulation, if we consider that PV to the power n equal to constant for the compression process, the generic reversible polytropic process. So, if we now just do some calculation, then we can write. So, we can write So, we can see so this is what we can see from this expression. So, if we consider this is the process which represents the compression process following a reversible polytropic one, and then we can see that del dP by dV is equal to minus n into P by V. So, what we could draw in the last class, that if we try to process or several processes in this PV plane, and if we need to raise the pressure from P1 to P2. So, this is say P equal to P1 and this is equal to P2, and then we can see that this is PV to the power n equal to constant. So, this is 1 to 2, and then we also can have another one process where n equal to 1, and the so this is the process 1 2, then 1 2 prime and 1 2 double prime. So, that means here if we consider gamma less than n less than 1, if this is the sequence, then we can understand this is basically Pv to the power gamma equal to constant, this equal to Pv is equal to constant, and certainly this is Pv to the power n equal to constant. So, what we can understand, if gamma is greater than n greater than 1, then in this PV plane whatever processes we could map, we can easily say that reversible adiabatic compression, this reversible adiabatic compression, that is Pv to the power gamma equal to constant, is steeper than the reversible isothermal compression. Hence, work input to the compressor, if the compression process follows reversible adiabatic one, then it would be high, and the minimum work would be needed for the reversible isothermal compression, but we have discussed that compression of any working fluid, whether it is air or any other gas, say for helium, if we need to say helium, if we need to compress it. So, compression process, if we need to consider reversible isothermal one, then this reversible isothermal compression is not of that much use, we have discussed, because in this type of compression we can only increase pressure, but temperature will remain more or less constant. So, this is what we can discuss. We can see that without going into much more mathematical analysis, just by using these relations, and mapping all the processes in this PV plane, we can see that reversible adiabatic compression is steeper than the reversible isothermal one. Hence, work needed under, if we hatch the area under that process line in PV plane, it would be much for the reversible adiabatic one. Okay. Now, what we would like to discuss today, that in the last class we have discussed about intercooling, and we had seen that. So, this is the first cylinder or LP cylinder, low pressure cylinder, that air is coming. So, this is intake air, and that is again taken to, this is intercooler, and from intercooler we are again taking the working fluid to another cylinder, that is high pressure cylinder. HP stands for high pressure, LP stands for low pressure, and finally that compressed air will be discharged so discharge at the discharge working fluid, and this is what is the process. Now, this intercooler, now it is, if we try to draw here, that discharge is again taken to the combustion chamber, and from there it is again taken to the gas turbine. Right. So, a case would have been like this: we are taking intake air to the low pressure cylinder, then we are taking that compressed air to this intercooler. From intercooler again, essentially what we are doing, we are reducing the temperature of the air before it enters into the second stage, compression, and finally the discharged working fluid is taken to this combustion chamber, or working fluid is discharged into this combustion chamber, wherein again by addition of it, its pressure and temperature increases and then it expands in the gas turbine and we are getting work output. And finally, this should be the final discharge. Now, what is important here to discuss, that we could discuss in the last class, that by mapping the processes in PV plane, we had seen that we can save certain amount of work input. Now, if we try to discuss the processes using a TS plane, then it will help us to understand, even though we can save certain amount of work input, still the efficiency using this intercooling unit reduces, and why it is reduced we shall try to now understand. So, if we try to plot the processes in TS plane, so this is P equal to P1, this is P equal to P2, right. A common process would be that this is the isentropic compression 1 to 2s, then again this is 3, this is 4s, and if we now consider that some degree of irreversibility will be there in both the compression and expansion process. So, this is 2 actual one, but this is this schematic. Say we are taking the air in this chamber and that compressed air is taken to this CC, that is combustion chamber. We are supplying certain amount of Q in and that is again taken to this and finally discharge. So, now this is gas turbine and this is CC stands for combustion chamber. Now, a case would be like this, that we are using single stage compression, but still would like to develop the same pressure, that is pressure ratio is same. We are taking intake air in the compressor, single stage compression going to the combustion chamber, again we are having some amount of heat addition to this working fluid and finally, we are taking that working fluid having high pressure, high temperature into this gas turbine unit and it will expand, working fluid will expand and we will be getting certain amount of work. Of course, to run this compressor, you know that shaft is connected, that is what we had seen. So, if we erase this one, that means this compressor is now connected to the gas turbine. Instead, what we are doing here, we are considering one intercooling unit we are having two different stages of compression, low pressure stage and then intercooling and a high pressure stage, finally to the combustion chamber and going to the gas turbine. The sole purpose is not to increase the temperature of working fluid substantially, which would be there if we consider single stage compression, and hence we can reduce the problems, or we can eliminate several problems, those will be there with the single stage compression. We have discussed all those. Then for a single stage compression, volumetric efficiency will be less, COP will be less, work input will be more, and then and also that degree of irreversibility will be more in this case for this single stage compression. So, what we are doing here, we are doing now this compression of the air using this intercooler or intercooling unit. So, now here, so this is cold water and this is hot water. Now, if we try to map the processes here in this TS plane, then you can see certainly in the low pressure stage turbine, pressure will increase from 1 to if we give name. So, this is 1, this is 2, then this is 3, this is 4, this is 5 and this is 6, right. So, 1 to 2 will be there, but you know that this is low pressure cylinder. So, compression ratio should be less. So, what we can do? We can assume that now what will happen if we this compression will be there up to an intermediate pressure, and we really do not know, let us assume this is the intermediate pressure. So, now this is this is the amount of rise in pressure in the low pressure stage compressor. Then what we are doing? If we go back to the previous slide, rising pressure of the working fluid we are taking that working fluid inside the intercooler. So, the temperature will reduce, and that reduction in temperature will be at constant pressure. Say this is the reduction in temperature up to this. So, this would be say 3, because here, so 2 to 3, that is reduction in temperature of the working fluid, and that is at constant pressure. That heat will be taken away by the cold water that is supplied to the intercooler. Then again 3 to 4 would be rise in pressure, that is from pressure 2. So, that means here we are trying to rise pressure from P1 to P2, and now again that pressure will be developed in a high pressure stage unit 3 to 4, that you can see from this schematic diagram 3 to 4, and then finally 4 to 5, that is the heat addition at constant pressure in the combustion chamber. We are assuming that, so that is pressure rise in this pressure rise of the working fluid at the end of the second stage of compression is equal to the rise in pressure by the single stage compressor. So, you can see that we could develop pressure from P1 to P2 by using these two different stages. We started from here, then up to this intermediate pressure, then again cooling, and then finally rising in temperature, and then finally this 4 to say 4 to 5, say this is 5, right, and we are assuming say this is again 3 to 5, and this 6. So, this could be 6s comma 6. So, as if again we are adding certain amount of energy to the working fluid by burning fuel, and we are able to supply equal amount of energy, and then it is again coming to that point and finally expanding in the compression in the turbine. So, what we can see from this particular depiction, what is the work input? So, work input is work input is with intercooling equal to Cp into what we can see work input Cp into T2 minus, so T2 minus T1, say this is also 2 here, right. So, this is 2 prime. So, T2 minus T1, then T1 plus Cp into T4 minus T3, because this is another work input. So, essentially 1 to 2 prime and then 3 to 4 prime, and work input without intercooling will be equal to Cp into like this. So, Cp into T2 or say I am right Ta minus T1. So, say this is, now I am giving a name, this is A. So, Ta minus T1. What we can do next? We can write that work input without intercooling equal to Cp into Ta minus T1. We can split it into Cp into, if we go back to this Cp into Ta minus T1, now we can split it Cp into T2 prime minus T1 plus Cp into T4 minus T3. So, we can split it Cp into T2 prime minus T1 plus Cp into Ta minus T2 prime, right, because just we are doing this algebraic manipulation here. Then you can understand, if we now write here that work input with intercooling, that already we have written in the previous slide, equal to Cp into, if we go to the previous slide, T2 prime minus T1 plus Cp into T4 minus T3, right. If we go back to the previous slide, that is what we had written in the previous slide. So, Cp into T2 prime minus T1 plus Cp into T4 minus T3, right. So, this is with intercooling and this is without intercooling, but the objective is to get equal pressure ratio, and we are also trying to supply the amount of heat for which, if we consider single stage compression, then heat addition will be T3 minus Ta or T3 minus Tas, that is depending on the actual or ideal cycle, or with intercooling it should be T3 minus T4, that is the heat addition. Okay. So, now if we compare these two equations, if this is equation number 1 and this is equation number 2, if we compare these two equations, then certainly following our previous discussion, that work input needed following reversible adiabatic compression, but using an intercooling unit is less than the work that would be required for the reversible adiabatic compression, but using a single stage compression, no intercooling effect. So, the first term, now if we consider here, this term is equal to this term. So, work input without intercooling and work input with intercooling. So, this quantity, I mean work input with intercooling should be less than work input without intercooling, provided this quantity is less than this, because this is common. So, that means we can write that work input with intercooling should be less than work input without intercooling, provided this Cp into this term T4 minus T3 is less than Ta minus T2 prime, right. So, we can write T4 minus T3 is less than Ta minus T2 prime. So, if this is a case, then only work input with intercooling should be less than work needed to compress the air without intercooling. It is also true, if we look at this Ts plane, you can see that constant pressure lines, we have drawn two constant pressure lines here, and we can see these lines diverge as we move from left to right, and hence it is easily understandable that Ta minus T2 prime is certainly greater than T4 minus T3, right. T4 minus T3 is this and Ta minus T2 prime is this. So, certainly Ta minus T2 prime is greater than T4 minus T3, that we can get from this Ts plane. So, here, so if we write, so this is, we can see that we can see from the Ts plane that constant pressure lines diverge as we move from left to right. So, this is true, and hence whatever we could establish in the last class from the PV plane, that saved amount due to intercooling is also getting justified from this analysis from by mapping the processes in a Ts plane. So, now this is this should be same, it is very important. Now, if we go to the previous slide, just if we look at this would be same as if this is a case that if we assume that efficiencies of both compressions, we are having compression in the low pressure cylinder and high pressure cylinder. So, that isentropic efficiencies of these two compressors operating separately are each equal to the isentropic efficiency of the single stage compression. So, that means in using an intercooling unit, what we are doing, we are essentially allowing air to be compressed following two different stages, and if we assume that the isentropic efficiency of both compressors, though they are working separately, and if they are each equal to the isentropic efficiency of the single stage compression, then this is true. Also, we can see from this Ts plane that these two lines diverge as we move from left to right. So, hence this Ta minus T2 prime is certainly greater than T4 minus T3, hence it is easily perceptible from this diagram that work input with intercooling unit should be less than work input without intercooling. Now, question is, this is okay. Now, as we have discussed in the last class, what would be the work ratio? Work ratio is defined as the work of or turbine work or expansion work, that is the positive work minus compression work divided by expansion work. What we can see from this analysis, that this work, so this is WC, this is WT and this is also WT. Now, WC is less for compression with intercooling. Hence, work ratio will be more. If this is less, then work ratio will be more for the compression processes or for the gas turbine unit having multi-stage compression. Question is, although we can ensure that the work ratio will be high, but still efficiency of the gas turbine units having multi-stage compression is less. Why it is so? We know efficiency is equal to net work output by the heat addition. What we can see from this, that again if we look at this TS plane, what is the amount of heat addition needed if we consider single stage compression, that is T3 minus TA if it is actual cycle, or it is T3 minus TAS if it is ideal cycle. But now heat addition which we need to supply to the combustion chamber to get equal amount of work output, in that case the heat addition should be T3 minus T4. Certainly T3 minus T4 is higher than T3 minus TA or T3 minus TAS. So, this extra amount of heat addition that should be there because of this intercooling effect will reduce the cycle efficiency even after achieving higher work ratio. So, the reduction in rather increase in heat addition that should be needed to run the unit having multi-stage compression with intercooling should be such that after having higher work ratio, the overall or gross impact is cycle efficiency reduces. Not only that, as we have discussed, for the intercooling unit we need to supply water or any other coolant, and for that again we need to have mechanical components. So, installation of those mechanical components as well as maintenance will eventually increase the total cost associated with this unit, and hence even though intercooling effect increases work ratio, but the gross impact is the reduction in thermal efficiency. I also would like to discuss another important issue that I forgot in the last class, that very important is what should be the intermediate pressure at which this intercooling effect will be performed. So, this intermediate pressure, that is this pressure line, right. So, this is intermediate pressure. So, this is intermediate pressure. This intermediate pressure should be such that the pressure ratio, that is P2 by P2 prime by P1 should be equal to P4 by P3. So, this is very important, that when we are talking about multi-stage compression, pressure ratio in each stage should be equal. So, intermediate pressure will be selected in such a way that for a multi-stage compression pressure ratio in each stage should be equal. So, just I am writing that this P2 prime by P1 should be equal to P4 by P3. So, this is basically a condition for the intermediate pressure. That means pressure ratio in each stage should be equal, right. So, this is I am writing here pressure ratio in each stage should be equal. Okay. Now, with this, let us now discuss about the combined cycle plant. So, combined cycle plant. The concept of combined cycle, from where it is coming, why it is needed. We all know that gas turbine units are largely used in aircraft fuel and propulsion, but still if you recall, we had discussed about the use of closed cycle gas turbine units, and typically closed cycle gas turbine units are used in captive power plant, gas cooled nuclear reactor, and sole purpose is to supply certain amount of energy as and when demand increases. And these gas turbine plants are known as peaking unit to supply certain amount of energy when demand increases. So, closed cycle gas turbine units are typically used in captive power plant, and these are known as peaking unit to supply certain amount of energy when demand increases. Now, question is, there are several disadvantages of gas turbine units. What are those? Large compression ratio, high exhaust loss, high degree of irreversibilities associated with both compression and expansion process, then low cycle efficiency that we have discussed. Even after increasing work ratio, it is not possible to increase cycle efficiency that we have discussed today. So, accounting for all these problematic issues, there are certain applications wherein gas turbine units are used, but still there are several advantages as well, because less installation cost and installation time, and also these gas turbine units respond quickly to the change in demand or load, and we can start quickly, you also can stop this unit quickly. So, now question is, despite having a few disadvantageous features, still there are some advantages, and accounting for this advantageous feature are new concept, that is the use of combined cycle. What is done here? We had seen that if we consider this is the compressor, then we are having combustion chamber, we are supplying certain amount of Q in, as if we are supplying fuel, and we are supplying certain amount of heat. So, basically in this unit we are having heat addition to the working fluid. So, this is compressor. So, and then this is so, and now so this is gas turbine unit, right, and this is heat exchanger, in which this is heat exchanger, this is heat exchanger, and here what is done, if we try to use So, we can see there are two cycles, one is known as topping cycle, another one is bottoming cycle. So, we had seen that in a gas turbine unit we have high exhaust losses. Had we not used the gas that comes out from the turbine to this heat exchanger, it would not have been possible to utilize that heat, it would not have been possible to recover that heat. Essentially what we are doing, we are taking the gas that comes out from the gas turbine after doing certain amount of work to this heat exchanger, wherein that gas which is having high temperature is taken away by this stream, that is water. So, here we are having this is H2O plus steam cycle and that is gas cycle, right. So, let me tell you, it is because of this high exhaust loss gas turbine units are having low cycle efficiency. Now, the idea behind this combined cycle is to utilize the heat or energy which will otherwise will be rejected to the ambience, and utilizing that energy we can run the steam cycle or steam power unit and we can run another steam turbine. So, we have discussed about steam power cycle and we had seen that boiler will be there, but here there is no boiler, but the amount of energy that will be released by the gas that comes out from the gas turbine in this heat exchanger to the working fluid, that is the water, that water will be converted into steam and it will again taken to the steam turbine wherein the working fluid will expand. So, water will be converted into steam, that steam will expand now in the steam turbine and we will be getting work output. So, here we are getting W out 1, we are getting W out 2, right. So, if we can run this unit, perhaps we are getting work output from the gas turbine, work output from the steam turbine, though certain amount of work that would be needed to be supplied to compressor here. So, that means if we draw here that, right. So, this is the common shaft. So, idea is to use two different cycles and two cyclic power plants are coupled in series to produce net work output, right. So, idea is to utilize the heat as I said you and utilizing that heat to run this bottoming cycle and that is the H2O cycle. So, topping cycle is gas cycle, bottoming cycle is H2O cycle, and by running these two cycles we can get the power, and as I said you gas turbines or closed cycle gas turbine unit, this is are known as peaking units, and these peaking units are used to supply certain amount of energy when demand increases. So, now if we go for some analysis, so what we can see, now we can see that there are two different cycles, one is gas turbine cycle, then gas turbine cycle you know that if we consider this is A, this is B, this is C and this is D. Similarly, we have this is 1, this is 2, this is 3 and this is this is 2, this is 2, this is 3 and this is 4, right. So, for the gas turbine cycle we can write Tc by Td, that is expansion, that equal to P2 by P1 power gamma minus 1 upon gamma. So, expansion process inside the gas turbine, as I said you that gamma for compression may not be equal to gamma for expansion, because we are adding certain amount of fuel here in real applications, and hence gamma and Cp will change. So, this is gas turbine cycle, this is for expansion, and for the compression we can write Tb by Ta equal to P2 by P1 power gamma minus 1 by gamma. Again I am telling, so this is for the compression. So, gamma for compression may not be equal to the gamma for expansion. Now, this is we can write, then what would be work output? So, work output from the gas turbine unit should be equal to m dot of the mass flow rate of the air into Cp gas expansion into Tc minus Td minus Cp into compression air into Tb minus Ta, right. So, what we are assuming? We are assuming, as I said you, that this gamma may not be equal, this Cpg and Cpa are not equal because those are different, and we are assuming mass flow rate of air only, because essentially when we will be getting work output we need to consider mass flow rate of fuel as well. So, ideally this should be m dot A plus m dot F, but if we consider higher fuel air ratio, higher air fuel ratio, sorry. So, for higher air fuel ratio, it is more or less m dot A, because fuel is very less. Now, what about steam turbine work output? Then work output from steam turbine cycle or steam power cycle that is WST equal to mass flow rate of steam into enthalpy drop H2 minus H3 that we had seen in our previous lectures, that is H3 minus H4, right. So, now question is we need to go for energy balance. For energy balance we have to draw the TS diagram, right. So, this is P condenser and this is P boiler. So, this is the 0.3, this is 0.4, this is 0.1, this is 0.2. So, this is steam power cycle that we had discussed many times before. Now, there is a topping cycle, and that cycle is in the TS plane is like this. If we try to draw using this color, right. So, right. So, this is C, this is D, this is A, this is B. So, this P equal to constant, this P equal to constant, and this is the heat addition Q in and this is Q out, right. So, I should write Q out gas turbine, so this is Q out gas turbine, right. Now, you can see that amount of energy released by the gas will be taken away by this or taken by the water, and it will be converted into steam. Okay. So, if we now do the energy balance, what we can write? Now, by energy balance we can write. So, basically amount of energy that we need to supply to run the gas turbine unit. What is this? We are supplying, this is Tc. So, if we go back to the previous slide, so basically that is the amount of energy available with the working fluid before it enters into the gas turbine, and finally that energy of the flowing stream, flowing gas is producing certain amount of work here, and then remaining energy is transferred to the bottoming cycle, that is the H2O cycle. So, we really do not know. So, we consider Tc minus say Tf. So, let us consider this is the point, this is the point F. So, this is the point F, right. This energy now would be equal to, this would be equal to m dot S into H3 minus H4, right. So, basically this is energy balance, energy supplied into the gas, that is equal to this m dot S Cpg into Tc minus Tf, that would be equal to m dot S into H3 minus H4. So, now then this is the expression we can write from the energy balance, right. So, part of that energy is producing gas turbine work, remaining part of this energy is utilized to producing steam turbine work. So, this is basically the energy balance. Now, what is Q in? Then Q in, that is equal to m dot A into Cpg into Tc minus Tb, right. So, this basically you know that is the amount of energy, you can see that Tc minus Tb, that is Q in, that is eventually that is the total addition of heat into this system having two different cycles. So, this is the Q in. So, the overall efficiency of the combined cycle eta overall equal to net work produced, that is steam turbine plus W gas turbine divided by Q in, right. So, this is what we can see from this. So, we could write the overall expression of the overall efficiency, and that is the total work output from both cycles divided by the total energy added to the system. So, now the advantage of this combined cycle is high overall efficiency, low water requirement, and then low environmental impact. So, though closed cycle gas turbine units are not used frequently for power generation, but closed cycle gas turbine units are connected in series with the steam power cycle to produce certain amount of load or to supply certain amount of load when demand increases. But despite having several disadvantageous feature of the closed cycle gas turbine unit, still when that unit is now connected in series with the steam turbine unit, we can have a few advantages like high overall efficiency, low environmental impact, and low water requirement. So, with this I stop here today, and we shall continue our discussion in the next class. Thank you.